AI-driven permeability prediction, a data-centric approach. Introduction. Introduction. The permeability is one of the most important engineering properties of soils as it governs the movement of water and water fluids through the soil mass. Accurate Accurate estimation of soil permeability is critical in geotechnical engineering for the design of foundations, earth dams, drainage systems, and other structures where fluid flow affects stability and performance. The direct measurement of soil permeability through laboratory or field tests can be time consuming, costly, and sometimes challenging due to variability in soil properties. As an alternative, indirect methods have been developed to predict soil permeability from more readily obtainable soil characteristics such as grain size distribution and plasticity indices. Grain size distribution provides insight into the texture and gradation of the soil, which directly influence the void space and connectivity through which fluids can flow. Plasticity data index plasticity data, including the liquid limit, plastic limit, and plasticity index, provide informative about the clay fraction and the soil tendency to retain water. Soil with higher plasticity tend to have lower permeability because clay particles can form a compact matrix that reduces the size of flow channels. The objective of permeability prediction from grain size and plasticity data is enabled engineers to quickly assess the soil behavior, plant drainage, and seepage control measures and perform preliminary geotechnical design. Advances in statistical modeling, regression analysis, and machine learning have further improved the accuracy of such predictions by integrating multiple soil properties into predictive frameworks. Permeability prediction with AI. Permeability or hydraulic connectivity is a critical soil property controlling water flow, groundwater movement, and seepage through soil layers. The traditional traditional predicting methods rely on laboratory testing, example constant head or falling head test, or empirical correlations based on grain size distribution and plasticity indices. However, these methods can be used time consuming and expensive, limited by sample representativeness, sometimes inaccurate for heterogeneous soils. With the growing availability of soil property datasets, artificial intelligence offers a promising alternative for rapid and accurate permeability prediction. AI approaches. AI techniques can learn complex nonlinear relationships between soil properties and permeability. Common approaches include like artificial neural networks. It mimics the human brain's ability to learn patterns. Input features can include grain size fractions, plasticity index, liquid limit, and void ratio, etc. Support vector machines. Use it for regression to predict continuous values like permeability, decision trees, and random forest. Divide into subsets based on feature thresholds. Gradient boosting and XGBoost. Ensemble learning methods that sequentially improve predictions, very effective for structured tabular data like soil datasets. Hybrid models combined AI with empirical equations or optimization algorithms. Examples: ANN trained using Cosmic-Karman parameters for improved accuracy. A workflow for AI-based permeability prediction. First one, data collection. Gather the soil samples. Gather soil samples with measured permeability. Collect corresponding properties, grain size and distribution, and plasticity index, and void ratio and porosity. Data pre-processing. Normalize or standardize features. Handle handle missing data. Optional augment data using the synthetic techniques. Validation and technique testing. Evaluate model performance using matrices such as mean squared error, root mean squared error, the coefficient of determination. And advantages of AI in permeability prediction can capture nonlinear and complex relationships between soil properties and permeability. It reduces the time and cost compared to laboratory tests, and it can handle heterogeneous soils where the traditional empirical models fails. And it allows for real-time prediction in engineering project. Challenges: it requires a large and diverse dataset to achieve accurate predictions. Model may overfit if the dataset is small or biased. In interpretably, it can be lower for complex AI models, example deep neural networks. Methodology. Methodology, there are different collections like data collection. In data collection, the soil sampling, it collects the representative soil samples from the study area, ensures samples over a variety of soil types: sand, slit, clay, and mixed soils. And laboratory tests determine the following properties for each example, like grain size distribution, Atterberg limits, liquid limit, plastic limit, and plasticity index, natural moisture content, bulk density, and void ratio, permeability using standard laboratory methods, example constant head or falling head test. And data pre-processing. In data pre-processing, the cleaning, it remove inconsistent of missing data points. And normalization or standardization, scale input features to a uniform range, example 0 to 1, to improve AI model training. Feature selection, to choose the relevant features for model inputs such as grain size, fractions, plasticity index, liquid limit, and void ratio or porosity. Model development, selection of AI models consider such as artificial neural networks, random forest, support vector regression, gradient boosting machines like GBM or XGBoost. Model architecture for ANN, input layer and hidden layer and outer layer. Training, use the dataset to fit the model, adjusting hyperparameters, learning rate, number of neurons, tree depth, etc. for optimal performance. Prediction and analysis, use the trained AI model to predict the permeability for new soil samples based on their grain size and plasticity properties. Compare predicted permeability values with laboratory measured values to assess reliability. Perform sensitivity analysis to identify which soil properties most significantly influence permeability. Sixth one, optional or hybrid approach. Combine AI predictions with traditional empirical formulas. Example, the Kozny-Kármán equation for improved accuracy. Results and discussion. First one, data overview. The dataset consists of soil samples collected from study location. The soil types range from sandy soils to clay soils with following characteristics. The sand content 25 to 85%, slit content 5 to 50%, clay content 5 to 35%, plasticity index 8 to 35%, measured permeability K with 10 power minus 7 to 10 power minus 2 meter per second. The wide variation in soil properties ensured that the AI model could learn relationships across diverse soil conditions. Third one, model performance. Multiple AI models were implemented including ANN, random forest, SVR, and XGBoost. The performance metrics on the testing datasets are summarized. And observations. ANN and XGBoost showed superior performance, indicating their ability to capture nonlinear relationships between soil properties. and permeability. The random forest performed slightly worse, likely due to overfitting on smaller subsets of soil types. SVR had the lowest accuracy possible due to the datasets norm, non-linearly and variation in feature scales. Prediction versus measured values. A scatter plot of predicted versus measured permeability for the ANN model figure shows the most data points closely aligned along the 1:1 line, indicating high predictive accuracy. Minor deviations occurred in soil with high clay content, where permeability is extremely low and more sensitivity to microstructure. Feature important analysis using random forest and XGB models that contribute of each soil properties to permeability prediction was evaluated. Evaluated. Feature Features and important: sandy content 35%, clay content 28%, plasticity index 20%, slit content 10%, liquid limit 7. A discussion: the grain size fractions, especially sand and clay content, had the largest influence on the permeability. Plasticity index also contributed significantly, reflecting the effect of clay mineralogy on water flow. The liquid limit and the slit content were less influential but still important for fine grained soils. Implications: AI based permeability prediction allows for rapid and reliable estimation without extensive laboratories tests. Sensitive soils with high clay content still require careful attention due to microscale effects not fully captured by bulk properties. Integration of AI models into geotechnical design can reduce cost and improve planning for drainage, foundation, and seepage analysis. Conclusion: this study demonstrates the effectiveness of using artificial intelligence to predict soil permeability from readily available soil properties such as grain size distribution and plasticity indices. In summary, AI-based permeability prediction offers a reliable, efficient, and scalable approach for understanding soil hydraulic behavior, bridging the gap between laboratory testing uh, and practical engineering applications. Thank you.